Hi everyone. I'm Mason, the programmer for 16379, the Kookybotz. A little bit of background about our team. We are a three-person team from Sammamish, Washington, competing since 2019. Competition-wise, we've been fortunate enough to compete at the Maryland Tech Invitation in the last 2 years, the Power Play World Championship, where we also won the Innovate Award. So for a little bit of an overview about what we're going to go over today, I'm going to be talking a little bit about our history with Swerve, which will cover our progression, as well as what is a coaxial swerve. And I'll be presenting a bit of a Swerve roadmap, which will cover the bare minimum and the things required to achieve maximum control over the robot. And for a brief introduction as to what these things are, they are first order kinematics, module PID, and motor flipping. And then for achieving maximum control, it's second order kinematics, position remembrance, slew rate limiting, and loop time optimizations. So first off, what is a coaxial swerve? This drivetrain design consists of 4 independently rotating traction wheels to maintain traditional holonomic capabilities while achieving unparalleled agility, speed, and maneuverability. The module rotation taking place is powered by a belt transmission from the servos, and the rotation is measured by an absolute analog encoder. Finally, the wheel rotation is powered by a coaxial shaft running through the middle of the swerve module. And here you can see 2 photos of the base plate, as well as the wheel assembly. We've always been dedicated to breaking the limits of what's possible in FTC, and this can be seen in both our hardware and our software. We went through 3 major iterations with our drivetrain design, coming up on our 4th right now. Each one of these iterations helped increase the efficiency, used more advanced manufacturing processes each time to increase durability. We also explored different materials to lighten modules and increase responsiveness of the modules. Version 1, the summer version, served as the proof of concept drivetrain. We wanted something that was responsive, not dealing with the setbacks of sacrificing the quality of other mechanisms on the robot. However, it still needed to be better. Version 2 solved nearly all of the major issues with the first version. The use of the axon servos directly allowed us to improve the responsiveness of the drive base by increasing the speed at which the modules rotate. This version was mostly 3D printed parts for the swerve module, such as a 3D printed core. Version 3 explored different manufacturing techniques and materials to create a lighter, more rigid, and more robust drivetrain. This was a combination of using billet aluminum, carbon fiber, and mark forged parts. And then here's a video of what the very first version of the Swerve looked like when driving. This is the summer version. This was the dual Go Build a Super Speed version, and as you can see, there are a lot of small issues with it, such as heading instability, random jittering, and more. This was largely in part due to the mass testing that this first design underwent, as well as static issues when originally filming this video. The first thing that we're going to cover is the overall structure of how we're going to set up things in the code. Typically, what we like to do is have 3 main classes. So one for the Swerve drivetrain, one for the module, and one for the absolute analog encoder. The drivetrain class is meant to handle all of the kinematics, as well as hold arrays of every single Swerve module that you have, so you can write data like wheel speeds and target rotations to every single module. Each module class will then store a motor, servo, absolute analog encoder, as well as a PIDF controller. Other constants that you could store in here are the PID constants, feed forward values, wheel radius, gear ratio, and ticks per revolution. This class acts as a clean way to handle reading the encoder, updating every value to every single part of the module, as well as handling every single property, such as whether or not you want your module inverted, how you're going to normalize values, things like that. And lastly, the absolute analog encoder class. This class stores the maximum voltage returned by your encoder. In the case of a plus series axon servo, that would be 3.3. With a Lamprey, I believe that's a 2.3. A few other values that are stored in here that we like to store are the offset, which is useful for just tuning the module to make sure they're all straight. Whether or not you want your module inverted, your readings inverted. We also handle the math here to take the voltage from the analog encoder and then convert it to a heading for where the module is. Just to elaborate a little bit on what we're covering today, I will not actually be showing any code. My goal with this presentation is to try and expose everyone to the concepts and things needed to try and get a bare minimum working coaxial swerve. Now that we've covered a little bit of the structure, though, we can go into first order kinematics. So the first thing we're going to do is start by looking at 2 free body diagrams of what the vectors on the swerve look like when you're turning and translating. With this free body diagram here on the left, you can see an example of the vectors generated with your controller input. And in this case, you want to be translating to the upper right direction, which is the blue vector, while also trying to rotate counterclockwise, which is the red vector. You'll want to then combine these, and that will get you this green vector, the combination of the two. You then use the magnitude of this vector, which is the velocity that you're setting to the wheel. And in this case, this can be done by simply getting the Pythagorean theorem, by getting the hypotenuse, and then you then plug that into the wheel speeds. With the angle, we take the arctangent of the y component over the x component of the green vector, resulting in a target heading in radians for our module. On the right, you can see a similar example with no translational vectors, but all just rotation. This would be rotating clockwise in this case. Unfortunately, I can't go super in depth here covering the inverse kinematics behind how these vectors are made, because if I did, then I wouldn't have enough time for the rest of the stuff in this presentation. Next, we're going to talk about module PID. Now, in order to get your module to fully rotate and react to when it has to move, you'll need some form of feedback from the module. The two big contenders on the market right now for feedback with coaxial swerves and FTC are the FRC Lamprey encoders and the Plus Series Axon Servo. Once you have this feedback as to where your module is, you'll use the same process that we described in the kinematics to get the target angle for your module. You will then plug this target angle in, along with the current heading of the module that we get from the encoder, into the PID controller, and the output of that will be sent to the servo rotating it. It is important to note that the servos are going to be in continuous rotation mode, as servo mode does not currently have the capabilities to do a near 360-degree rotation, so you'll have to use CR mode for now, although there are no drawbacks at all to using it. One thing to note about these is that when you're tuning the module PID, you'll want your swerve down on the ground, because if you tune it while the modules are up in the air, you're not running them against that surface, so as soon as you start running it on the ground, you'll run into some weird behavior and it won't work accurately. Finally, for the bare minimum, we're going to be talking about motor flipping. Now picture this. If you move your stick forward and you're suddenly driving in one direction, forward for example, and then you instantly want to move your stick backwards, as if you want to go in the opposite direction, what would happen to the modules? Well, the target heading would essentially flip by 180 degrees. Now the issue with that is that your modules are going to be rotating 180 degrees, which will make you have to wait for them to fully rotate before you can continue driving. This is not the most optimized movement. The way around this is by checking if the error between your target and current heading is greater than pi over 2, in which case you then want to subtract pi from your target heading, normalize, and then recalculate the error. You then, once you get this new heading, you plug it into the PID controller and invert the velocity being set to the wheel. That way you don't have to do a full 180-degree rotation, but just flip the wheel speeds. One of the biggest complaints heard when it comes to FTC swerve is modular rotation being a setback. This change does a great job of reducing the magnitude of this issue as module rotation is taken account into in the calculations. When you want to translate and rotate around the field, the feeling of the swerve being jerky will be extremely reduced. It is important to note that this is not a necessary change. It is just one that might be beneficial for you if your hardware isn't super great. Then again, that doesn't mean software fixes should be the solution for bad hardware. I also want to bring up this clip again. A lot of the skew with the heading in this likely would have been solved with basic second-order kinematics. Not fully, but it definitely would have made it more drivable. A little optimization I made to the software during the middle of the season is something I call position remembrance. As an example, during power play, imagine you were trying to make small adjustments on a pull. If you are a driver who likes to flick the joysticks and is just a little speedier in general, you might have difficulty trying to adjust to a pull, since with a swerve, your modules will constantly be spinning, resetting back to your zero position over and over again. A simple fix to this that completely negates the issue with micro adjustments is just always caching the heading value you are setting to the modules. And as soon as your joystick, you detect that the joystick goes back to 0, your dead zone, meaning that you've let go of the joystick, you write back that same cached heading value to the modules. This means that heading will be maintained all the time until you rotate the modules yourself. This same concept can be applied to heading on the robot, making it easier for the swerve to maintain its heading around the field when translating and rotating. Slew rate limiting is the process of smoothing out input. This can be applied to joysticks to create joystick curves. So for example, if you are someone who, as mentioned earlier with position remembrance, likes to flick the joysticks, this can help smooth out your input. This reduces the instantaneous acceleration and overall allows for smoother driving. To elaborate a bit, this is often a preference thing. Some people find it useful, others don't. And here's an example of what that looks like here. Red would be the example of what your input might look like for your stick if you were to just instantaneously flick it to the right, for example. And then green would be the smoothed out version of that. Lastly, loop time optimizations. So using something like an Axon servo, for example, they update internally at 333 Hertz. This means that in order to get the full capabilities of the servo for a more reactive experience when driving, and just in general, you want to get your loop times as fast as possible. I'm going to list a few optimizations that can help you achieve this goal. However, not all of them are necessary, as they could potentially lead to dangerous software, causing random crashes or bugs. For example, our loop times were in the range of 250 to 400 updates per second this season. We were able to accomplish this by moving every device that can be bulk read onto one hub. This means that instead of having to bulk read both hubs, we only do one, significantly helping how fast our loop times are. Another large change we made was with multi-threading the IMU. IMU reads can take upwards of 2 to 3 milliseconds, which means your program halts during that 2 to 3 millisecond period. By threading it, we effectively remove this stop, reducing our loop times even more and allowing our program to continue as normal. Overall, making sure you cache values, reduce the amount of new objects made, as well as write clean code can help lead you to best possible performance. And two things I would like to end on. As of right now, I'm currently working with FTClib, a very popular FTC library that I'd highly recommend using to bring Swerve Kinematics to a more widespread platform in FTC. So if you're interested in building a coaxial Swerve drivetrain and don't want to do all the heavy lifting, although I would highly recommend learning it, it's a lot of fun. Keep an eye out for that. That might be released. And as you obviously know, I wasn't able to go super in depth with this as of obviously time constrained. So I will be releasing videos to our YouTube channel, Kookybotz on YouTube, very soon in the coming weeks, which will go far more in depth on the math, inverse kinematics, basically everything that we had to cover. And I think that's everything I have. Thank you for listening.